All right, so we've only got one learning target today, but it has two parts: identify and use cross sections of three-dimensional figures. And even though we're in Unit 12, which is at the end of the book, we're going to start on page 67. You don't even have to turn to page 67 if you don't want to, because everything you need is up here. But let's start off talking about these three-dimensional figures, okay? A solid with all flat surfaces that enclose a single region of space is called a polyhedron. Each flat surface, which is called a face, is a polyhedron, okay? So in a polyhedron, it's a three-dimensional figure. It's a solid. We're going to call it solid, okay? So it's a solid with where each flat surface is a polygon, and those flat surfaces are called faces. The line segments where the faces intersect are called edges. The edges of the solid are the sides of the faces. So it gets confusing, right? What we've always called sides all year long are now edges of this polyhedron, okay? And then the point where three or more edges intersect is called a vertex. So where the segments intersect is the vertex. So try not to call the faces sides because it gets confusing. If I say, well, look at that side there, you'll be wondering, is he talking about the flat surface, which is called a face, or is he talking about the segment, which is called an edge? The word side doesn't really apply. Now, having said that, you know what we'll say a whole lot? We'll say side, okay? And we really shouldn't, but we will, at least I will, because I'll lapse back into calling things what we've called them all year long. So let's try to pay attention to context and realize if we're talking about a face or an edge. And then we have different types of solids. So it says below are examples and definitions of polyhedrons and other types of solids. So these first two I have here are polyhedrons. And these are the two types of polyhedrons that we will spend some time with finding volume. A prism, that's with an M, not an N, not J, is a polyhedron with two parallel congruent faces. Now, if you look at the figure here, this pentagon here, and then this pentagon down here are congruent to each other and they're parallel to each other. They're called the bases. So a base is and I'm trying not to be Dr. Seuss, but it ends up sounding Dr. Seuss's anyway. A base is a type of face. Bases are faces that are congruent and parallel. That's the least Dr. Seuss I can make that sound, okay? So we understand what bases are. Now, the bases are connected by parallelograms. So the other faces are parallelograms. Quite often they're rectangles, okay? But there's some type of parallelogram. Now, a pyramid is a polyhedron that has a polygon for its base, and then all the other faces are triangles. Now, the number of triangular faces depends upon how many edges the base has. If the base has 3 edges, there will be 3 triangular faces. If the base has 7 edges, there will be 7 triangular faces. And the triangular faces all meet at one point. That one point where they all meet is called the vertex of the pyramid. If you just visualize a pyramid, you're probably going to think of a square pyramid. Most people do, where the square is the base. Now, these two types of solids are named after their bases. If the base in the case of a pyramid, bases in the case of a prism, are pentagons, we call them pentagonal pyramid or pentagonal pyramid or prism. If the bases are hexagons, hexagonal pyramid or hexagonal prism. Okay? So, those are the types of polyhedrons we're going to be working with. Somewhat familiar with those? All right. We're going to have some that are not polyhedrons. Look at those figures. Tell me why they're not polyhedrons. Yeah, because then not everything's a polygon. They have curved surfaces, not just flat surfaces. So you've got a cylinder. Now, a cylinder and a cone are both with a circular base. A cylinder is a solid with congruent parallel circular bases connected by a curved surface. And then a cone is a cylinder that just has one base, not two. All right? And where the curved surface comes to a point, that point's called the vertex. So cylinder, cone, bases are circles. Cone has one base, cylinder has two bases. And then a sphere is a set of points in space that are the same distance from a given point. All right, a circle was a set of points in a plane equidistant from the center point. A sphere is the set of points in space. In other words, 3 dimensions, all equidistant from the center. Okay? So, any questions? All right, eventually what we're going to do is we're going to find volumes. You don't have to write these down yet. We will concentrate on these one at a time starting tomorrow. But you've probably seen these formulas. And if you haven't, that's okay too. And you may have seen a different version of these formulas. I'm going to give you a slightly different version for some of these. Okay? But one thing we've got to concentrate on, and the reason I put this slide on here, is you can't freelance with your letters. If it's a capital B, that's different than a lowercase b. If you notice here, capital B stands for the area of a base, area of a polygon or a circle, okay, because that's what the bases are. So don't use lowercase b. Lowercase b is the base of is one side of a polygon, isn't it? It's an edge of a polygon. So I noticed back when we were doing areas of regular polygons, some of you used lowercase a to stand for area, which became a problem when your formula was area equals 1/2 apothem times perimeter. You had 2 lowercase a's in one equation meaning different things, and that can be confusing. Don't do that now, okay? If the formula says capital B, it's capital B, okay? Now, to page 821. So go ahead and turn to page 821. All right, this is kind of the intro to chapter 12 here. You know that in a right triangle, one of the sides is an altitude. However, in an obtuse triangle, the altitude is outside of the triangle. So look, here's the idea. In this right triangle, that red segment's the altitude. In this obtuse triangle, that red segment's the altitude. So the altitude can be outside of, in the exterior of the triangle. A prism with lateral edges that are also altitudes is called a right prism. In other words, lateral means side. So if the edges that do not make up part of the base, they're the lateral edges. The edges that do not make up part of the base are the lateral edges. If they are perpendicular to the base, then it's a right prism. If the lateral edges are not perpendicular to the base, it's an oblique prism. Then similarly, if the axis of a cylinder, take a guess. For a cylinder, what do you think the axis is? The segment that connects what, would you guess? The centers of the circular bases. Good. That's what the axis is. Similarly, if the axis of a cylinder is also the altitude, in other words, if the axis, the segment connecting the centers of the circular bases, is perpendicular to the circles, then it's a right cylinder. Otherwise, it's oblique. Now, let's make sure we can identify these. So if you look here, this first one, A, that's a right prism because this would represent a lateral edge, Well, it's perpendicular to the square bases. And if it's perpendicular to one of them, it'll be perpendicular to both of them because the square bases must be parallel. That's the definition of the prism, that the bases are congruent and parallel. Okay? So since you can find one lateral edge that's perpendicular to one base, that means all the lateral edges are perpendicular to both of the bases. It's a right prism. Look at B here. It's oblique because look, there's a lateral edge. Thank you. There's the axis, is really what I need to look at, isn't it? The axis. It's not perpendicular to either circular base, so oblique. And then you see here, that's a right cylinder, because if I drew in the axis, it'd be perpendicular to both of the circular bases. Oblique prism, oblique cylinder. Questions? Yes. Well, and sometimes it's hard to tell because they'll take a right one and tilt it at an angle, like if I did that, then you're supposed to recognize that it's still a right one. But notice they have a little perpendicular mark in there. That helps. So this one's oblique because this lateral edge is not perpendicular to this base. And I don't know, it depends on how they draw it, right? Kind of hard to tell. All right, any other questions? All right, now, our learning target for today was all about cross sections. A cross section, so let's see, what page am I on now? I'm on page 824. A cross section is the intersection of a solid and a plane. Think of it as taking a plane and slicing the solid into two parts, okay? In fact, they used to be called slices. At least in calculus, we used to call them slices. Now we call them cross sections like everybody else does. The shape of the cross section formed by the intersection of a plane and a three-dimensional figure depends on the angle of the plane. This is going to take a little bit of abstract reasoning from you to figure out what the cross section looks like. Okay? But if you look here on this pyramid, if you take a horizontal cut, so you start with a plane that's horizontal. Okay, so in other words, if that pyramid is sitting flat on the ground, it's perpendicular. That plane then is not perpendicular, parallel to the square base. Well, if you cut it like that, and then just imagine that you could actually take the top of that pyramid off. You sliced it in two, you take the top of the pyramid off, and then you take the two pieces and you turn them towards you and you look at those cross sections. You look at the place where the pyramid was cut in two. What would you see? Well, it'd be a square. But if you angle it differently, like this, and you did the same thing, you took those two pieces, you pulled it apart, you turned the cross section so they're facing your eyes, and you looked at them, you see triangle. Because this little section right there isn't as long as this section there. It's a trapezoid. Okay? You sliced it vertically. You can get a triangle. Now, some of these are fairly hard to visualize. Okay? And some of them aren't. Let's take a look at this. All right, here we have a prism. What's the shape of the base? Pentagon. They're regular pentagons. Okay? And see where the cross section's cut out here? Right now, it's a regular pentagon because notice that the way they must have this done is the cross section is parallel to the bases. When the cross section is parallel to the bases, the shape of the cross section will be the same shape as the base. Okay? But let me start moving this cross section around a little bit. Look over here. This graph on the right is showing you what the shape of the cross section is. Over here is showing you where they're cutting it from. Would you have thought you'd get that as a cross section? No, you have to cut it at a strange angle, right? Not one that you would probably think to do yourself. Let me show you this part right here. All right, I'm not sure I've got it just right. I think I do. If I'm making this cross section exactly vertical, isn't the cross section a rectangle? Okay. If it's really vertical, I'd get a rectangle over there. And when it's off vertical just a bit, it's not a rectangle, it's a trapezoid. Okay? So the normal cross section that you get from this kind of a figure would be the pentagon with the horizontal cut, a rectangle with the vertical cut, and then a trapezoid where it's not vertical, not horizontal, just angled. But as we see here, those aren't the only kinds we can get. We can get some really odd-looking pentagons out of here. Okay? Let's take a look at the pyramid. We just get some general quadrilateral there, don't we? There we've got a hexagon. Wow, I didn't see that coming. It keeps going back. Trying to get it back to where it's a regular pentagon. All right. Now, watch this. So the cross sections parallel to the base are cross sections of regular pentagon. We get different sizes of that regular pentagon depending upon where we make the slice. Well, that seems reasonable, doesn't it? Since the pyramid's a lot larger at the bottom than it is at the top. Will that same thing happen with the prism? No. The cross section now, since it's parallel, right? When I move the cross section up and down, it doesn't matter because the prism is the same width at the bottom as it is at the top and everywhere in between. And then I won't belabor the point, but with the cylinder, that's going to happen, right? Those circles are going to be the same all the way. With a cone, it's going to matter. All right, they're all circles as long as the cut's parallel to the base. And then, of course, if the cut's not parallel to the base, you get what are called conic sections that you'll study later on in your math life. Ellipses, and then parabolas. So remember when you get to, I don't remember if it's in Algebra 2, maybe in pre-cal, you do conic sections. Remember the stupid little animation I showed you? And then same thing with a cylinder. Ooh, did you see the rectangle coming? If you make a vertical cut, you get a rectangle again, don't you? Okay? All right. That's when you get things called hyperbolas. All right. So you're going to have to do some imagining to imagine these cross sections. Okay. All right. Let's do a couple of examples. You don't have to write this one down. Ramona has a cake pan shaped like half of a sphere, known as a hemisphere. From geography, hemisphere. As shown at the right. Doesn't everybody have a cake pan that's in the shape of a hemisphere? How do you put that in the oven? I mean, wouldn't it go... Anyway. Describe the shape of the cross sections of the cakes baked in this pan if they are cut horizontally and vertically. Cut horizontally, the slices would be parallel to the circular base. What would you get? Circles. And if you went vertically, what would you get? Not squares, because the top would be rounded, you would get semicircles. All right. Now, do write these down. They're part of your assignment. So turn over to page 825, and we'll start with number 5. Describe how the cheese at the right can be sliced so that the slices form each shape. So they're asking it backwards. Instead of telling you how to cut it and asking you what the shape is, they're saying, excuse me, how would you slice this to get a rectangle? If the cross section is going to be a rectangle, what would you do? Parallel to this, right? So vertically. And by the way, you don't have to get all, it's either going to be vertical, horizontal, or angle. All right? So vertical. So slice. Yeah, they assume we're going to slice it. I'm just going to say vertical. Vertical. All right, how would we get triangles? Horizontal. Make it parallel to the triangular bases. Make it horizontal. And how would you get a trapezoid out of that? Angle. It'd be kind of like this. We could have that and that. Trapezoid. So, angle. Number 6. Describe each cross section. So back to they're showing you how to cut it. You have to figure out what it would look like. So if you make a vertical slice, what happened with the vertical slice of the prism on the animation? Rectangle. So, rectangle. And number 7, you make that horizontal slice, but I'd think of it this way. Maybe I can't. How did I? Yeah, I'll just do it. That's really kind of the way I'd rather look at a cone, right? Think of it as sitting on the circular base, making a vertical cut, and I'm going to see a triangle. So, all right, any questions? All right, on page 825, do 5 through 7. Those shouldn't take you very long. 15 through 19, 21, 25 through 28, 35, 40 through 46, and 48 through 50.